pendulum manifold. In this exercise, we consider a classical pendulum described by these state equations. And for the first question, I have to observe first that when I increase theta by 2k pi, then the two states are, of course, identical. And from this, I have to deduce what is the shape of the state space. Okay. So I consider my pendulum, which is like this. Okay. This is the angle named here theta, and omega is the velocity. I represent like this. So of course, the pendulum can go at the top. What I can see here is the state equation. So the derivative, the state, is theta omega, and the derivative is directly linked to the state itself, omega and theta. So here it is due to the gravity, which a force like this, and this is due to the friction, this one. So this pendulum is stable. Now, of course, I understand that if I add 2 pi to theta, then the state will be exactly the same, whereas in this representation, theta will be different. So it is a problem for many applications. I want the same theta. So what happened is that theta in this representation, given here, theta is like this. So theta, 0, 2 pi, and my theta represented here is here, but I don't know if I am here, here, or somewhere else. So what we do usually, we form an equivalence relation like this, which say that two angles theta and theta, so theta and let's say theta 1 and theta 2 are equivalent if theta 1 minus theta 2 is equal to 2k b, like this. So it is equivalent to say that P1 minus P2 divided by 2kb, like this, this number is, excuse me, not the k, belongs to z. So the set of integer, which can be negative. So it means equivalently that theta 1 minus theta 2 belongs to 2pz, like this. So if this is the case, then they are equivalent. So it is an equivalence relation, so reflexive, symmetric, and transitive. And due to this, I am able to build the set of angles. The set of angles will be defined as R, the set R, like this, presented here, divided, so the quotient with this relation theta, or equivalently, it is denoted like this, 2 pi z, like this. So it means that this one, R, this one is R, will now, if I make this quotient, will now be transformed into a disk like this. So 0, and it is the same as if I cut here, and I put this one, I glue this point here. So all this is not necessary, but just to remember that this corresponds, it can be seen as a symbol to represent the unit disk. So in this case, theta now is represented as an element of R divided by 2pz. Now, omega can be as I want. Omega can be as fast as desired. So omega belongs to R. Can be positive or negative, big or small. There is no periodicity like this. So I have this. And the state theta and omega belongs to the Cartesian product, so R divided by 2pz, the Cartesian product with R. And this is a disk, and this is a line. So a disk like this, with 0, and a line like this, with 0. Okay. If I make the Cartesian product between this set and this set, I obtain a cylinder. So the cylinder can be represented like this. And goes to infinity and minus infinity. Here it will correspond to the 0. And one point in this cylinder, I can associate theta, which corresponds here to this angle, and also an omega. So the state does not belong as previously defined as an element theta omega is not an element of R2, but theta and omega is an element of this cylinder. Question number 2. I set 3 new variables x1, x2, x3, and I have to give the state equation in this x space. And I should also write the constraint that should satisfy x. So what is the idea behind this? I had at the beginning 2 variables, theta and omega. They live in a cylinder. And to draw the cylinder, I will need a 3-dimensional space. So x1, x2, x3, even if the cylinder has 2 variables, so it is a 2-dimensional manifold. And the concept behind this, it is the notion of immersion. What is an immersion? An immersion, it is a representation in Rn, so something which is have higher dimension, of a manifold. Manifold is some kind of surface. And in this picture, we have the representation of the Klein bottle, which is a manifold of dimension 2. So it's dimension 2 because I am only allowed to move inside the surface of this bottle, but to draw it, I have to immerse or to do the immersion inside the 3-dimensional space. So it is what I will do here. So this was I had my cylinder, and question number 2. I have x1, so x1, x2, x3 my variables, and they are given by x1 is equal to cos theta, this one is equal to sine theta, and the last one is given by omega. Now, to build the state equation, I have to express the derivative of x as a function of x. So it is what I want to obtain. So for this, I will write the derivative. X dot 1 is equal, after I will do for x dot 2 and also for x dot 3. So x dot 1 is equal to, so I will compute the derivative of this one, and it is minus sine theta multiplied by the derivative of theta, but theta dot, I recall that it is equal to omega. Here, multiplied by omega. Here it will be either cos theta multiplied by omega, and for the last one, I will have minus sine theta minus O half of omega. So this one is equal to minus x2, x3. This one is equal to x1, x3. And this one is equal to minus x2 minus half of x3. So I have expressed this, or this, as a function of x1, x2, x3. So it is f of x. In this representation, I have also to say that this one, x1, comes from the cosine, and x2 is a sine of theta. So I have to add a constraint which states that this one square plus this one square is equal to 1. So I have to add the constraint x1 square plus x2 square equal to 1. Okay, so let me recall what I have done. I have here the space x1, x2, x3. I have my cylinder like this, which goes to infinity. Okay. The state should satisfy this, so it means this is the equation of this cylinder. So this one corresponds to this one. So a consistent state should be inside this cylinder. If I am outside, it means that I am not consistent with my system. So I have always to satisfy this. So x1, x2, x3 is the extended state space. So let me check. It is important to check that if the initial condition is on the cylinder, then I will stay in the cylinder forever. Of course, it will be the case, but I want to verify it. So if at time t equal to 0, I satisfy x1 square 0 plus x2 square 0 equal to 1. So it means I am on the cylinder. Then I want to check that for all t, I have x1 square of t plus x2 square of t is equal to 1. I want to check this. For this, I will consider this the function which called surface. S of x, I define like this. It is equal to x square plus x2 square. So when S of x is equal to 1, it means that I am on the surface. So what I need to check is that the scalar product, so the scalar product of the gradient of S with f of x should be equal to 0. So it means that I need to check that f of x here is always tangent to the cylinder. Okay, so that's what I want to check. So the gradient is like this. It is orthogonal like this. So this corresponds to the gradient derivative with respect to x of S of x. It's a row. It is orthogonal, of course. So to check this, I will compute the gradient of S of x, and I will make the scalar product with f of x, and to check that it is equal to 0. So this is equal to here 2x1 and 2x2. So I compute the gradient of this, and I multiply by f of x, which was given here, like that, here. And it is given by minus x2, x3, x1, x3, and Whoops, excuse me, here I have to add a 0, of course, due to plus 0x3, of course. And minus x2 minus x3, like this. So I make the computation, and I get 2x1 multiplied by minus x2 x3 plus 2x2 to do this multiply by x1 x3 plus the 0 here multiply by minus x2 minus half of x3. So this is equal to 0, and this plus this is equal to 0, so it means that all is equal to 0. So I have checked that f of x is tangent to the cylinder. Question number 3, I have to provide a Runge-Kutta simulation on the x1, x2, x3 space, and the initial vector to be chosen is given here. I have to draw the corresponding trajectory and give the interpretation of the results. I propose to use this library given here. And so this program will generate an OBJ file. So I will use 3dviewer.net to visualize it, so there is nothing to install. So I draw the axis, so it will be axis for x1, x2, x3, and I will use the function draw cylinder. So I need a matrix here, and I will now explain here. To draw the cylinder, I take a basic cylinder where all dimensions are equal to 1. So let's say it's like this. The basic cylinder is oriented like this, and the radius is equal to 1, and here it will go from -1 to +1. So if I want a cylinder, for instance, corresponding to my manifold, I will have I want a cylinder that go from let's say -6 to +6. So for this, I will transform by a represented like this, ax plus b, and what I want is a cylinder like this, from 6 to -6. This is why I will take for b something equal to 0 here, and for a it will be a diagonal matrix, which will be 1, 1, because I don't want to change the radius, and 6, and zeros everywhere. So this is what I do here. I will draw it green, and this is a transparency, O.8. I switch to Python, I run the program, and the file has been generated. So I will go to 3dviewer.net, I open my file, and I have here. Now I want to draw the vector field. So I have my cylinder here, I have my function f of x here, and recall that f of x is given by minus x2, x3, x1, x3, and minus x2 minus O.5, x3. Okay, so for this, I will have to take points everywhere in the cylinder and to draw the corresponding arrows, like this, to have an illustration of this function f, which is interesting for me, but only on the cylinder, not outside. Okay, so for this, I draw my cylinder first, here, and then I will take theta in the trigonometric circle So from 0, so theta, from 0 to pi with some different step. So the step here is chosen as pi divided by 10. And for omega, so omega will be this direction, omega. It corresponds also to x3. And here recall that I have x1, x2. Then for omega, I will go from minus 6 plus 6. So here it corresponds to 6. So for this, I will first consider this vector. So 1, 0, omega. This one. So 1, 0 is like this. And 1, 0, omega is somewhere like this. So where here it corresponds to the omega I want. And now from this, I am in this plane, of course. And I will have to rotate it. And to rotate it with an angle theta. And for this, I will use the Rodriguez formula, which takes the exponential matrix into account here. And this will perform the rotation I want to go at the right place, for instance, here. And once I will be here on x, so x1, x2, x3, I will call f of x and draw the arrow. So at point x, x is given here, I will draw the arrow here, given here. It's f of x. I put here a normalization vector to avoid to have some very long arrows, just for the visualization. So I will put something almost equal to 1, except when it is small. So it is due the role of this factor in front of f of x. I switch to Python. This is my program. I run it. I generate the file. I come to the viewer. And I get the representation I wanted. So we can see different things. The vector field is turning around the x3 axis. Here I have an equilibrium point at this point here, which looks stable. We can check here. It looks stable. So the trajectory will converge to it. And the other one looks unstable. We can see that there is some direction of the field that bring me to this equilibrium point, but some other direction that get me out of this equilibrium point. I have some kind of saddle point, and this point is unstable. So this one means that the pendulum is at the top. For the integration, I will use a Runge-Kutta method given here and represented by this equation. Okay, so how it works, I assume that I am here at time t, so here it is x of t. This arrow corresponds to f of x of t. So I will apply first a short-term integration to have a new vector, and the Runge-Kutta method makes some kind of average between this evolution and this evolution, and the error is normally small. So the trajectory that will be generated inside this loop will follow the arrows and will be like this. So probably here it goes like this, follow the arrow, go behind, will come back, and this like this. But sometimes it start far. Maybe I can do several turns before reaching the equilibrium point. So this is the program. I run it. It generates the OBJ file. I go here. I open it. it takes more time to open. I have more and more things to draw. And I have here my trajectory. From the top here, I start here. And after I turn around, and then I will converge to the equilibrium point given here. But when I zoom, I see something that I don't like. Due to numerical error, I go out of the cylinder. And it is a problem when I compute with an immersion. And for this, I will have at each step to project on the cylinder. And it is what I will do now. Assume that my vector x is here. So here I recall that I have x1, x2, and x3. So I don't want to change x3. I just want to change x1, x2, and to project here. Okay. So for this, say like this. So only x1, x2. So I will compute the distance to of this vector x equal to x1, x2, x3, and this distance is given by x1 square plus x2 square. Then I will renormalize the two first components on x to compute this projection. Only the two first one. I don't want to change x3. So it is what I do here. This one, I will call it n, and I will normalize only the two first components, not the last one. And for this, I am sure that the trajectory will remain on the cylinder. I run the program, I generate my file, I open it, and we'll see now that the trajectory is always on the inside the surface, inside the cylinder. Okay. So I have less errors. So for the simulation, I have started from x0, which is equal to minus 1, 0, 6, which corresponds to this point. It also corresponds, this one to the cosine of theta, and this one to the sine of theta, and here the speed, omega. So it means that the pendulum was like this, at the bottom, like this, with a very huge speed like this, of 6. And it can only turn like this on this circle. So this one is fixed. So we can see here that in the trajectory, that the pendulum has turned like this, one turn. Here, when it is here, it means it after one turn. Then after one turn, it comes back, oscillate like this, and at the end is able to finish at the bottom. Okay, we have this illustration near the equilibrium point, so we can see that we had some oscillation before reaching this point, and this point corresponds to the situation where the pendulum is at the bottom. It is a stable equilibrium point.